What's going on? Let me continue with the book on page 98. Like this, int asterisk px semicolon is intended as a mnemonic. It says that the combination asterisk px is an int. That is, if px occurs in the context asterisk px, it is equivalent to a variable of type int. In effect, the syntax of the declaration for a variable mimics the syntax of expressions in which the variable might appear. This reasoning is useful in all cases involving complicated declarations. For example, like this, says that in an expression a to f and asterisk dp have values of type double. You should also note the implication in the declaration that a pointer is constrained to point to a particular kind of object. Pointers can occur in an expression. For example, if px points to the integer x, then asterisk px can occur in any context where x could set y to 1 more than x, prints the current value of x, and produces indeed the square root of x, which is coerced into a double before being passed to scored. See chapter 2. In expressions like this, the unary operators asterisk and ampersand bind more tightly than arithmetic operators. So this expression takes whatever px points at address 1 and assigns to it y, and assign it to y. We will return shortly to what this might mean. Pointer references can also occur on the left side of assignments. If px points to x, then sets x to 0 and increments it as does. The parentheses are necessary in this last example. Without them, the expression would increment px instead of what it points to, because unary operators like asterisk and plus plus are evaluated right to left. Finally, since pointers are variables, they can be manipulated as the other variables can. If py is another pointer to int, then py equal px copies the contents of px into py, thus making py point to whatever px points to. 5.2 Pointers in function arguments. Since C passes arguments to functions by call by value, there is no direct way for the called function to alter a variable in the calling function. What do you do if you really have to exchange an ordinary argument? For example, a sorting routine might exchange two out-of-order elements with a function called swap. It is not enough to write where the swap function is defined as because of call by value, swap can't affect the arguments a and b in the routine that called it. Fortunately, there is a way to obtain the desired effect. The calling program passes pointers to the values to be changed. Since the operator ampersand gives the address of a variable, ampersand a is a pointer to a. In swap itself, the arguments are declared to be pointers, and the extra operands are accessed through them. Like this, one common use of pointer arguments is in functions that must return more than a single value. You might say that swaps returns two values, the new values of its arguments. As an example, consider a function getInt which performs free format input conversion by breaking a string of characters into integer values. One integer per call, getInt has to return the value it found, or an int, a while signal when there is no more input. These values have to be returned as separate objects for no matter what value is used for EOF. That could also be the value of an input integer. One solution, which is based on the input function scanf that we will describe in Chapter 7, is to have getInt return EOF as its function value if it found in a file. Any other returned value signals in normal integer the numeric value of the integer it found is returned through an argument, which must be a pointer to an integer. This organization separates end-of-file status from numeric values. The following loop fills an array with integers by calls to getInt. Hang on. Each call sets v to the next integer found in the input. Notice that it is essential to write $v instead of v as the argument of getInt. Using plain v is likely to cause an addressing error, since getLine believes it has been handed a valid pointer. getInt itself is an obvious modification of the A to I we wrote earlier. Throughout getInt, *pn is used as an ordinary int variable. We have also used getch and nggetch described in Chapter 4, so the one extra character that must be read can be pushed back onto the input. Exercise 5 middle score 1, right? getFloat, the floating point length of getInt. What type does getFloat return as its function value? 5.3 Pointers in arrays. In C, there is a strong relationship between pointers and arrays, strong enough that pointers in arrays really should be treated simultaneously. Any operation which can be achieved by array subscripting can also be done with pointers. The pointer version will in general be faster, but at least to the uninitiated, somewhat harder to grasp immediately. The declaration, like this, defines an array of size 10. That is a block of 10 consecutive objects named A*0, A*1 until A*9. The notation A*I means that the element of the array I positions from the beginning. If PA is a pointer to an integer, declare it as int*PA, then the assignment PA equal ampersand a bracket 0. Set PA to point to the zeroth element of A. That is, PA contains the address of A bracket 0. Now the assignment x equal a asterisk PA will copy the contents of A bracket 0 into X. If PA points to a particular element of an array, then by definition PA plus 1 points to the next element, and in general PA minus I points I elements before PA, and PA plus I points I elements after. Thus, if PA points to a bracket 0. A asterisk parenthesis PA plus 1 refers to the contents of a bracket 1. PA plus I is the address of a bracket I, and asterisk parenthesis PA plus I is the contents of a bracket I. These remarks are true regardless of the type of the variables in the array A. The definition of adding 1 to a pointer, and by extension all pointer arithmetic, is that the increment is scaled by the size in storage of the object that is pointed to. Thus in PA plus I is multiplied by the size of the objects that PA points to before being added to PA. The correspondence between indexing and pointer arithmetic is evidently the correspondence between indexing and pointer arithmetic is evidently very close. In fact, a reference to an array is converted by the compiler to a pointer to the beginning of the array. The effect is that an array name is a pointer expression. This has quite a few useful implications. Since the name of an array is a synonym for the location of the zeroth element, the assignment like this can also be written as like this. Rather more surprising, at least at first sight, in the fact that a reference to a bracket I can also be written as a asterisk parenthesis a plus I. In evaluating a bracket I, C converts it to a asterisk parenthesis a plus I immediately. The two forms are completely equivalent, applying to the pointer ampersand to both parts of this equivalence. It follows that ampersand a bracket I and a plus I are also identical. A plus I is the address of the i's element beyond A. Here's the other side of this coin. If PA is a pointer, expressions may use it with a subscript. PA bracket I is identical to a asterisk parenthesis PA plus I. In short, any array and index expression can be written as a pointer and offset, and vice versa, even in the same statement. There's one difference between an array name and a pointer that must be kept in mind. A pointer is a variable, so PA equal A and PA plus plus are sensible operations. But an array name is a constant, not a variable. Constructions like A equal PA or A plus plus or P equal ampersand A are illegal. When an array name is passed to a function, what is passed in the location of the beginning of the array within the called function. This argument is a variable, just like any other variable. And so an array name argument is truly a pointer, that is, a variable containing an address. We can use this fact to write a new version of string, which computes the length of a string, like this. Incrementing is perfectly legal, since it is a pointer variable. S++ has no effect on the character string in the function that called string, but merely increments string's private copy of the address. It has four more parameters in the function definition. Chars s bracket semicolon and char asterisk s semicolon are exactly equivalent. Which one should be written is determined largely by how expressions will be written in the function. When an array name is passed to a function, the function can, at its convenience, believe that it has been handed either an array or a pointer, and manipulate it accordingly. It can even use both kinds of operations if it seems appropriate and clear. It is possible to pass part of an array to a function by passing a pointer to the beginning of the sub-array. For example, if A is an array and both pass to the function f the address of element a bracket 2, because ampersand a bracket 2 and a plus 2 are both pointer expressions that refer to the third element of a within f, the argument declaration can read like this or this. So as far as f is concerned, the fact that the argument really refers to part of a larger array is of no consequence. 5.4 Address Arithmetic. If p is a pointer, then p++ increments p to pointing. Then p++ increments p to point to the next element of whatever kind of object p points to, and p plus equal I increments p to point I elements beyond where it currently does. This and similar constructions are the simplest and most common forms of pointer or address arithmetic. C is consistent and regular in its approach to address arithmetic. Here is integration of pointers and its integration of pointers, arrays, and address arithmetic is one of the major strengths of the language. Let us illustrate some of its properties by writing a rudimentary storage allocator, but useful in spite of its simplicity. There are two routines. A log returns a pointer p to n consecutive character positions. Hang on. which can be used by the caller of a lock for storing characters. Free releases the storage, thus acquired. Free releases the storage, thus acquired. Free releases the storage thus acquired so it can be later reused. The routines are redemptory because the calls to free must be made in the opposite order to the calls made on a lock. Free releases the storage thus acquired, so it can be later reused. The routines are redemptory because the calls to free must be made in the opposite order to the calls made on a lock. That is, the storage managed by a lock and free is a stack or lasting first out list. The standard C library provides analogous functions which have no such restrictions, and in Chapter 8 we will show improved versions as well. In the meantime, however, many applications really only need a trivial lock to dispense little pieces of storage of unpredictable sizes at unpredictable times. The simplest implementation is to have a lock hand out pieces of a large character array, which we will call a lock buff. This array is private to a lock and free, since they deal in pointers, not array indices. No other routine need know the name of the array, which can be declared external static, that is local to the source file containing a lock and free, and invisible outside it. In practical implementations, the array may well not even have a name. It might instead be obtained by asking the operating system for a pointer to some unnamed block of storage. The other information needed is how much of a lock buff has been used. We use a pointer to the next free element called alloc p. When alloc is asked for in characters, it checks to see if there is enough room left in alloc buff. If so, alloc returns the current value of alloc p, i.e. the comma at the beginning of the free block, then increments it by n to point to the next free array. Free merely sets alloc p to p if p is inside alloc buff. Some explanations in general, a pointer can be initialized just as any other variable can, though normally the only meaningful values are null, discussed below, or an expression involving the address of previously defined data of appropriate type. The declaration defines alloc p to be a character pointer and initializes it to point to alloc buff, which is the next free position when the program starts. This could have also been written like this: since the array name is the address of the zeroth element, use whichever is more natural. The test like this. Check if there is enough room to satisfy a request for n characters. If there is, the new value. Hang on. If the request can be satisfied, a lock returns the normal pointer. Notice the declaration of the function itself. If not, a lock C must return some signal that no space is left. C guarantees that no pointer that validly points at data will contain 0. So a return value of 0 can be used to signal an abnormal event. In this case, no space, we write null instead of 0. However, to indicate more clearly that this is a special value for a pointer, in general, integers cannot meaningfully be assigned to pointers. 0 is a special case. Tests like this and this show several important facets of pointer arithmetic. First, pointers may be compared under certain circumstances. If P and Q point to members of the same array, then relations like less, greater than, etc. work properly. P less than Q is true, for example, if P points to an earlier member. If P points to an earlier member of the array, then does Q. The relations equal and exclusive equal also work. Any pointer can be meaningfully compared for equality or inequality with null. But all bets are off if you do arithmetic or comparisons with pointers pointing to different arrays. If you're lucky, you'll get obvious nonsense on all machines. If you're unlucky, your code will work on the machine but collapse mysteriously on another. Second, we have already observed that a pointer and an integer may be added or subtracted. The construction P plus n means the nth object beyond the one P currently points to. This is true regardless of the kind of object P is declared to point at. The compiler scales n according to the size of the objects P points to, which is determined by the declaration of P. For example, on PDP 11, the scale factors are 1 for char, 2 for int and short, 4 for long and float, and 8 for double. Pointer subtraction is also valid. If P and Q point to members of the same array, P minus Q is the number of elements between P and Q. This fact can be used to write yet another version of strlen, like this. In its declaration, P is initialized to S, that is, to point to the first character. The while loop, each character in turn is exempt until the \0 at the end is seen. Since \0 is 0 and since while tests only whether the expression is 0, it is possible to omit the explicit test, and such loops are often written as like this. Because P points to characters, P++ advances P to the next character each time, and P minus S gives the number of characters advanced over. That is the string length pointer arithmetic is consistent. If we had been dealing with floats which occupy more storage than chars, and if P were a pointer to float, P++ would have advanced to the next float. Thus we could write another version of a log which maintains, let us say, floats instead of chars, merely by changing chars to float throughout a log C and free all the pointer manipulations, automatically taking into account the size of the object pointed to. So nothing else has to be altered other than the operations mentioned here, adding or subtracting a pointer and an integer, subtracting or comparing two pointers. All other pointer arithmetic is illegal. It is not permitted to add two pointers or to multiply or divide or shift or mask them, or to add float or double to them. 5.5 character pointers and functions. A string constant written as is an array of characters in the internal representation. The compiler terminates the array with the character \0 so that programs can find the end. The length in storage is thus one more than the number of characters between the double quotes. Perhaps the most common occurrence of string constants is as arguments to functions, as in printf hello world. When a character string like this appears in a program, access to it is through a character pointer. What printf receives is a pointer to the character array. Character arrays, of course, need not be function arguments if message is declared as the statement assigns to message a pointer to the actual characters. This is not a string copy. Only pointers are involved. C does not provide any operators for processing an entire string of characters as a unit. We will illustrate more aspects of pointers and arrays by studying two useful functions from the standard iSnapshot library to be discussed in Chapter 7. The first function is struct_pi. The first function is struct_pi, which copies the string t to the string s. The arguments are written in this order by analogy to assignment when one would say to assign t to s, the array version is first. For contrast, here is a version of struct_pi with pointers. Because arguments are passed by value, struct_pi can use s and t in any way it pleases. Here there are conveniently initialized pointers, which are marched along the arrays a character at a time until the \0, which terminates t, has been copied to s. In practice, struct_pi could not be written as we showed it above. A second possibility might be like this. This moves the increment of s and t into the test part. The value of asterisk t++ is the character that t pointed to before t was incremented. The postfix ++ doesn't change t until after this character has been fetched. The same way, the character is stored into the old s position before s is incremented. This character is also the value that is compared against \0 to control the loop. The net effect The net effect is that characters are copied from T to S up to and including the terminating \0. Okay, here. As the final abbreviation, we again observe that a comparison against \0 is redundant. So the function is often written as like this. Although this may seem cryptic at first sight, the notational convenience is considerable. Hang on. And the idiom should be mastered. If for no other reason than that you will see it frequently in C programs. The second routine is scheme, which compares the character strings F and T and returns -0 or positive according as S is lexicographically less than, equal to, or greater than T. The value returned is obtained by subtracting the characters at the first position where S and T disagree. The point version of the scheme like this. Since plus plus and minus minus are either prefix or postfix operators, other combinations of asterisk and plus plus and minus minus occur, although less frequently. For example, asterisk plus plus p increments p before fetching the characters that p points to. Asterisk minus minus p decrements p first. Exercise 5 mid score 2. Write a pointer version of the function structure which we showed in chapter 2. Structure copies the string t to the end of S. Exercise 5 mid score 3. Write a macro for Mr.π. Exercise 5 mid score 4. Rewrite appropriate programs from earlier chapters and exercises with pointers instead of array indexing. Good possibilities include getLine, chapter 1 and 4, A to I, I to A, and their variants. Chapters 2, 3, and 4, reverse chapter 3, and index and getTop chapter 4. 5. The 6 pointers are not integers. You may notice in other C programs a rather cavalier attitude toward copying pointers. It has generally been true that on most machines a pointer may be assigned to an integer and back again without changing it. No scaling or conversion takes place, and no bits are lost. Regrettably, this has led to the taking of liberties with routines that return pointers, which are then merely passed to other routines. The requisite pointer declaration. The requisite pointer declarations are often left out. For example, consider the function strsafe, which copies the string s into a safe place obtained by a call on a lock and returns a pointer to it. Properly, this should be written as like this. In practice, there would be a strong tendency to omit declarations. This will work on many machines since the default type for functions and arguments is int, and pointer can usually be safely assigned back and forth. Nevertheless, this kind of code is inherently risky, for it depends on details of implementation and machine architecture which may not hold for the particular compiler you see. It is wiser to be complete in all declarations. The program named will warn of such constructions in case they creep inadvertently. 5.7 Multi-dimensional arrays. C profile is for rectangular multi-dimensional arrays. Hang on. Although in practice, they tend to be much less used than arrays of pointers. In this section, we will show some of their properties. Consider the problem of date conversion from day of the month to day of the year and vice versa. For example, March 1 is the 60th day of a long leap year and the 61st day of a leap year. Let us define two functions to do the conversions. Day of year converts the month and day into the day of the year. And month day converts the day of the year into the month and day. Since this later function returns two values, the month and day arguments will be pointers. Sets m to 3 and d to 1. These functions both need the same information, a table of the number of days in each month. 30 days has September. Since the number of days per month differs for leap years and non-leap years, it's easier to separate them into two rows of a two-dimensional array than try to keep track of what happens to February during computation. The array and functions for performing the transformations are as follows. Okay, like this. The array date tab has to be external to both day of year and month day, so they can both use it. Date tab is the first two-dimensional array we have dealt with in C. By definition, a two-dimensional array is really a one-dimensional array, each of whose elements in an array, hence subscripts are written as like this rather than this. As in most languages other than this, a two-dimensional array can be treated in much the same way as in other languages. Elements are stored by rows. That is, the rightmost subscript varies faceted as elements are accessed in storage order. An array is initialized by a list of initializers in braces. Each row of a two-dimensional array is initialized by a corresponding sublist. We started the array date tab with a column of 0 so that month numbers can run from the natural 1 to 12 instead of 0 to 11. Since space is not at premium here, this is easier than adjusting indices. If a two-dimensional array is to be passed to a function, the argument declaration in the function must include the column dimension. The row dimension is irrelevant since what is passed is, as before, a pointer. In this particular case, it is a pointer to objects which are arrays of 13 ints. Thus, if the array date tab is to be passed to a function f, the declaration of f would be like this. The argument declaration in f could also be like this. Since the number of rows is irrelevant, or it could be like this, which says that the argument is a pointer to an array of 13 integers. The parentheses are necessary since brackets have higher precedence than asterisk. Without parentheses, the declaration like this is an array of 13 pointers to integers, as we shall see in the next sections. 5.8 Pointer arrays, pointers to pointers. Since pointers are variables themselves, you might expect that there would be uses for arrays of pointers. This is indeed the case. Let us illustrate by writing a program that will sort a set of text lines into alphabetic order. Our stripped down version of the Unix utility sort. In chapter 3 we presented a shell sort function that would sort an array of integers. And the same algorithm will work, except that now we have to deal with lines of text which are of different lengths and which, unlike integers, can be compared or moved in a single operation. We need a data representation that will cope efficiently and conveniently with variable length text lines. This is where the array of pointers enters. If the lines to be sorted are stored end-to-end in one non-character array maintained by a log, perhaps, then each line can be accessed by a pointer to its first character. The pointers themselves can be stored in an array. Two lines can be compared by passing their pointers to circum. When two out-of-order lines have to be exchanged, the pointers in the pointer array are exchanged, not the text lines themselves. This eliminates the twin problems of complicated storage management and high overhead that would go with moving the actual lines. Sorting. The sorting process involves 3 steps. As usual, it's best to divide the program into functions that match this natural division, with the main routine controlling things. Let us defer the sorting step for a moment and concentrate on the data structure and the input and output. The input routine has to collect and save the characters of each line and build an array of pointers to the lines. It will also have to count the number of input lines, since that information is needed for sorting and printing. Since the input function can only cope with a finite number of input lines, it can return some illegal line count like -1. If too much input is presented, an output routine only has to print the lines in the order in which they appear in the array of pointers. Like this. Words so long. The new line at the end of each line is deleted, so it will not affect the order in which the lines are sorted. And like this. No, like this. The main new thing is the declaration for the line picture. Says that line PTR is an array of lines elements, each element of which is a pointer to a char. That is, line PTR bracket I is a character pointer, and asterisk line PTR bracket I accesses a character. Since line PTR is itself an array which is passed to right lines, it can be treated as a pointer in exactly the same manner as our earlier examples, and the function can be written instead as like this. Asterisk line PTR points initially to the first line. Each increment advances it to the next line, while n lines is counted down. With input and output under control, we can proceed to sorting. The shell sort from Chapter 3 needs minor changes. The declarations have to be modified, and the comparison operation must be moved into a separate function. The basic algorithm remains the same, which gives us some confidence that it will still work. Hang on. Okay. Since any individual element of V alias line PTR is a character pointer, TEMP also should be, so one can be copied to the other. We wrote the program about as straightforwardly as possible, so as to get it working quickly. It might be faster. It might be faster, for instance, to copy the incoming lines directly into an array maintained by read lines, rather than copying them into line and them to a hidden place maintained by a log. But it's wiser to make the first draft something easy to understand and worry about efficiency. Later. The way to make this program significantly faster is probably not by finding an unnecessary copy of the input lines. Replacing the shell sort by something better like quicksort is more likely to make a difference. In Chapter 1, we pointed out that because while and for loops test the termination condition before executing the loop body even once, they help to ensure that programs will work at their boundaries, in particular with no input. It is illuminating to walk through the functions of the sorting program, checking what happens if there is no input text at all. Exercise 5 middle school 5. Rewrite read lines to create lines in an array supplied by main rather than calling a log to maintain storage. How much faster is the program? 5.9. Initialization of pointer arrays. Consider the problem of writing a function month name which returns a pointer to a character string containing the name of the nth month. This is an ideal application for an internal static array. Month name contains a private array of character strings and returns a pointer to the proper one when called. The topic of this section is how that array of names is initialized. The syntax is quite similar to previous initializations, like this. The declaration of name, which is an array of character pointers, is the same as line PTR in the sorting example. The initializers is simply a list of character strings. Each is assigned to the corresponding position in the array. More precisely, the characters of the ith string are placed somewhere else, and a pointer to them is stored in name bracket I. Since the size of the array name is not specified, the compiler itself counts the initializers and fills in the correct number. 5.10 Pointers vs multi-dimensional arrays. Newcomers to C are sometimes confused about the difference between a two-dimensional array and an array of pointers, such as the name in the example above, given the declarations. Like this, the usage of A and B may be similar in that A bracket 5 and B bracket 5 are both legal references to a single int, but A is a true array. All 100 storage cells have been allocated, and the conventional rectangular subscript calculation is done to find any given element. For B, however, the declaration only allocates 10 pointers. Each must be set to point to an array of integers. Assuming that each does point to a 10-element array, then there will be 100 storage cells set aside, plus the 10 cells for the pointers. Thus, the array of pointers uses slightly more space. It may require an explicit initialization step. But it has two advantages. Accessing an element is done by indirection through a pointer rather than by a multiplication and an addition. And the rows of the array may be of different lengths. That is, each element of B need not point to a 10-element vector. Some may point to 2 elements, some to 20, and some to none at all. Although we have phrased this discussion in terms of integers, by far the most frequent use of arrays of pointers is like that shown in Mon's name, to store character strings of diverse lengths. Exercise 5 middle school 6. Rewrite the routines day of year and month day with pointers instead of indexing. 5.11 Command line arguments. In environments that support C, there is a way to pass command line arguments or parameters to a program when it begins executing. When main is called to begin execution, it is called with 2 arguments. The first, conventionally called argc, is the number of command line arguments the program was invoked with. The second, argv, is a pointer to an array of character strings that contain the arguments 1 per string. Manipulating these character strings is a common use of multiple levels of pointers. The simplest illustration of the necessary declarations and use is the program equal, which simply equals its command line arguments on a single line separated by blanks. That is, if the command equal hello world is given, the output is hello world. Okay, guys, it is time for me to take a short break. See you.